I love coming here. So much of life is about finding your people, and I spent a long time trying to figure out where my people were, and they're here.
My name is Nicolai Josuttis, and we have to talk. We have to talk about the C++ filter view. The title of this talk is Taming the C++ filter view, which of course implies a message, which is there are issues or there are surprises. You might say this is well in the tradition of C++, but first of all, it's interesting to see what are the surprises and where do we have to be careful. And the other thing, of course, is why. So let's talk about the filter. So assume we have a print function, a generic print function takes in const, a t reference argument, which is a collection, and let's print out the elements just one by one with a space. And we can pass a vector, we can pass a set, and there are some improvements, just in case you don't know them all. Since C++20, you can use auto instead of a template parameter, and you can even qualify this auto with a concept. So to constrain this function template, it's still a function template for something. So now we have here another new feature, and that is we can use views. So here's an example. Let's only print the first 3 elements of the first collection. Or let's print the first 3 elements of the second collection. And as you see, we are still using the generic print function, which uses the range-based for loop to iterate over the elements. Well, there's a more interesting syntax, which uses a pipe symbol. And that means you can pipe the collection into this view to take the first 3 elements. And with that, you can create pipelines like, let's take the first 3 elements and transform them into strings and append an s, and let's iterate over that. And as you see, we can print out all these elements. That is great power. That's composition of little pieces of computation and bringing together a lot of magic and power to deal with collections. So here are a few other examples, just so that you know this. This is a map of composers of classic music, the name and the year of birth. Let's iterate over these composers, but not over all of them. Let's only use those who were born since 1700. And then let's take only the first 3 of them. And then let's only take the views, the keys of that, which are the names of these composers. And that is what we use to pass to the range-based for loop on the right-hand side as our range. And voila, you have the output. Yeah, don't be surprised. The map is sorting the element. OK. Yet another example, we have a source view that's called iota, which generates values from 1 to 2, 3, and so forth. This can be unlimited. And let's filter these elements, only use multiples by 3. Let's drop the first 3 of them. Let's take the next 8 of them and transfer these values into strings, append an s, and use that on the right-hand side of the filter view of the range-based for loop, and that's the output. We're so glad that we have auto standardized in C++ 11 because this is a type. Yeah, it's not only unit auto because of lambdas are involved. It's an iota view of a filter view, of a drop view, of a take view, of a transform view. OK. Good. Why do I have the same slide twice? I have no idea. So you can use these pipelines also to modify elements. So here's another example. Let's create a view, just a filter, and let's have some words. in a string, and let's print out all the elements. And now let's iterate with the filter using this view to say, I'm only dealing with the elements that are not empty. And you see that at the end, each and every string has an index now, while the one in second last one doesn't have an index. So how does this work? And that's important to know to understand how you have to deal with that. In principle, it's easy. We have the most successful feature of C++ is iterating over values, over elements. And it's using a general API we have with all the data structures, which is iterators. You get them with begin and end, and you can iterate over the values by calling ++ and comparing with the end and using the star to go to the value. So the range-based for loop, if it is used, is calling a low-level loop using that iterator, letting that iterator iterate over the elements from begin to end. And that's like raw pointers do. So we call begin to have the first element. While we are not at the end, let's print out the value, go to the next element. While we are not at the end, go print out the value, go to the next element, and so on and so on. And that's the way this works. Now assume we use a view. So now let's do the same in the following situation, calling print. And we pipe all the elements to a filter, only allowing the elements less than 20 and transforming each and every element. So the way this works is that we, to some extent, create a filter view and then pass this filter view to a transform view, and both, as you see, wrap the existing container. So if you create the filter view, you are not starting to compute something, to process some elements. You only create a data structure. And that data structure is kind of a wrapper around the underlying range, which is a vector here. And this wrapper provides the same API as the underlying range, as every range. You can iterate from begin to end and accessing the values with star. And then here it is how it looks like. Good. So we have the wrapper iterating from begin to end and going to the next element. That's all possible. That did not happen yet. So when you then wrap this again with the transform view, you wrap the filter view, providing again an API to iterate from begin to end with an iterator. So far, nothing starts, nothing happens so far. So it's not like in Unix, where we just, when we have a pipe, we start to generate values, store them somewhere, and then the next component is starting to process these. So the game starts when I start to iterate. So when I call begin, I go to the outside view, which is the transform view, and that view asks the filter view for the begin, and the filter view asks the underlying collection, the vector for the begin. And now we're not done with begin yet, so the collection returns the position of the 47, of the first element. That position is passed to the filter. The filter says, oh, wait a minute, before I let this go, before I let this through, I have to look at the value of it. So I call star here, and the filter calls star for this position of 47 and rejects that. How does the filter reject? It calls ++, which means go to the next element. We are still inside begin of the filter. So the collection then gives back the position of the 11. The filter looks at it and accepts it. And that is passed as the first position. The position, not the value. To transform, transform just says, yeah, I pass everything through. If you just want to have an element, I come into play when you ask for the value. So that is what we return. And now we can double check and compare it with end. And then with star, we can access the value. And that means we go along this whole iterators to iterator to iterator, look at the value, but transform. The transform iterator will say, wait a minute, when you ask for the value, let me negate that. Go to the next element means we pass through the whole queue and say, let's go to the next element. Why we are not at the end, go to the value. Why we are not at the end, go to the value, print it out, and so on. And that's it. So the filter just makes sure we don't use each and every element. The transformation says, when you need the value, I negate it. So this is what we call a pull model. The next element and its value are processed on demand. That's a totally different approach than in Unix, where we have the push model. Good. You can see the same with some output. You can see that. Let's have some output in the filter and the transformation. You see, so far, this program doesn't print anything. Just when I start to iterate over the elements, you see a filter looks at 8, then it's 15, then it's passed to transform, then we get the value, and so on, and so on. It's interesting. There's a first consequence of this, which is let's change the order of the filter and the transform. So let's start with the transformation and then the filter. And that means you get the following behavior. Let's print out just a header, a starting tag, and then let's start to iterate. So we ask the filter for the begin. Beginner goes to transform. Transform goes to the collection. 8. Transform looks at 8, negates, passes the element 8 to the filter. The filter says, I need the value. So the filter goes back to transform. Transform asks for the value in the collection, gets the 8, the value, negates it for the filter. The filter looks at it and says, that's not less. Then that's not something I want to have. That's not a multiple of 3, what I'm looking for here. So the funny thing is that now the transformation, now the filter asks for the next, with plus plus. Transformation asks with plus plus for the next element, 15. Transformation negates that. That is passed to the filter so that the filter can decide whether to accept this element. This time the filter says yes after calling star for this, and then passes out the element, not its value again. The element. So now we come. Now the call, the begin call is done, the first begin call of this range-based for loop. So in the range-based for loop, we then say, but let's go to the value. Well, the filter looked at the value already, but that's gone. We only got the position. So in the range-based for loop, we look at the value again. So that's a second time we have to transform the value. And that is modulo optimization. Has the effect that if you put a filter behind a component like a transformation, the transformation might be called twice, might be done twice. So, and that happens with all the values that are passed through. And the more filters you put in the chain, the more often you have to do transformation. So, filters need the value to check. The caller needs the value again to process. We don't pass through values, we pass elements at positions, so iterators. First consequence, use filters early, avoid expensive stuff before using them. But don't be too nervous. Compilers optimize a lot. So if you have something like this, like let's iterate over a range that is passed to a filter, then passed to transform, like here, let's here say, okay, let me compile that. And compilers might throw away all the calls, just inline all the calls. So it's more or less something like iterating from begin to end, and you have an if saying, is the current position of the element, is the current value of the position a multiple of 3? If yes, process it, negate it. And if you change the order, you switch to code where you say, if the negated current position, the negated value of the current position is a multiple of 3, then process the negated current value. And whether this is a problem or not depends on compilers and optimization. But of course, in this case, it's not a big issue. But if the transformation is big and the compiler does not optimize anything here, then it can matter. Which means let's talk about the filtering and the filter view. Well, let's talk about the performance of filtering first. When we introduce data structures in C++ so that we can provide the API for begin and plus and so on, we came up with the idea that we harmonize the way we iterate over the elements. So you might have a vector, you might have a list, totally different data structures, but we have a couple of things in common and guaranteed, which is declaration default initialization is cheap. And begin is cheap. It's just because begin is, we have a pointer to the first element or so. End is cheap, which is the position behind the last element. Empty is cheap, because if begin is equal to end, then it's empty, otherwise not. Size is cheap, because we track size. Well, no, that's not true. We not always track size. There are some containers where we don't track size, exactly one, by the way, which is the forward list. You know that. So forward list does not have size. So because it's not tracked, and it would be expensive to ask how many elements do you have by iterating over all the values. And the index operator is also cheap or not provided. So that's a principle. We have the principle either it's cheap or we don't provide it. Well, sometimes we have things that are more expensive, but then we try to make sure that they look ugly and dirty and take time and effort. Yeah, there's a reason reinterpret cast, the most dangerous cast, has the longest word. That's intentional. That's not a joke. Okay, now when we learned that, let's look about what does happen when we use a filter view. Now, assume we have a vector here and we put a filter view on this vector and we call begin. Okay, that's easy. We go to the begin of the filter, but that's not enough because the filter, as you saw, has to double check, is this really the first right element? So we have to iterate over all the element values until we find a matching element. So begin is no longer cheap. When this is the last element in the container, it's a linear operation. 1 million elements, and you filter and to find the last is 1 million times calling plus and star and comparing against the end. And the same is true for lists. So in a list, then let's pipe into a filter. We have the same. Let's call begin and then call plus to go to the next element. We have to look at each element, so we really have to look at all of them to find out, yeah, the first matching element, here we look which one is greater than 9, is the element with the value 47. So begin is expensive, which means, in more technical term, a linear operation. And in both cases, just in general, in a filter, and that's natural, because we don't know where the first matching element is. So let's look at in more general and see, yeah, let's see. Okay, we have a declaration default initialization. That is cheap. Nothing happens there, just initializing a data structure. Begin can be expensive. For the same reason, end can be expensive. So we have to iterate to the last element or behind the last element. We could iterate from the end backwards if that's supported. But anyway, it's still can be expensive depending on where the end is. Empty can be expensive. Empty is more or less calling begin and see whether it's the end. And the operator, the index operator, size is expensive, and the index operator is expensive. These two operations have to iterate over all elements, or a couple of elements. So if you call the index operator to go to the 10th element, you have to do 10 times find the next element. That fits. we don't like bad performance. That's why we sometimes turn these operations off in APIs, which we have done with containers by not providing the index operator for lists. We do the same for filters. So in a filter, there's no size anymore. So yeah, you have a new container here that has no size. And you will probably use it way more often than a forward list. And the index operator is not there. And by the way, there's another consequence. The iterators that the filters use cannot compute where the 10th element is. They have to iterate to the 10th element, which means we don't like expensive jumps. So we say the iterators a filter provides are not random access iterators. You can only go forward and backward element by element. Okay, that has consequences for generic code. So if you have a vector and you're initializing a filter that, for example, looks for even elements, that means, yes, please don't compare the size with 0 if you want to check whether something is empty. Let's use empty instead, because that's supported by the filter. Again, that's nothing new for those who write serious, and even unserious generic code and knowing everything, because otherwise you would rule out the forward list container. Nobody uses the forward list. No, that's not right, but it's very rarely used for some reason. And as I said, of course, you cannot sort the elements, passing that to a sort algorithm, because we have no random access range. Okay, so good. Take a break, take a breath. That's just the introduction.
In this case, size and empty are really the same. There's really no...
In this case, size and empty is really the same. Well, the effect is what we check is the same, but the problem is size is not supported by a filter, so it will not compile. So it's not the same.
Performance-wise.
Yeah, performance-wise, it's the same, yeah. Yeah, okay, we come to that. Okay, so now let's iterate over the elements of a filter view. So guess we have something, underlying container, where we have some elements. Let's here have 30 elements, and we are looking for every 7th element. So let's use the filter for that, and we find the 6 and the 13 and the 20 and the 27. So you would expect that the filter says, okay, I have begin at the 6, I have end at the position behind the 27, and I have that way I have a way to iterate. Plus plus is not just going to the next element, it might skip a couple of elements until it fits. There are different ways to deal with that. One is you can use the range-based for loop. The range-based for loop, as you see it here, internally uses a for loop. And that for loop at the beginning calls once begin and once end. And that way, then we iterate over that. So we just looked at the price of begin, and we saw begin is no longer cheap for a filter view. So, but we call it only once. That's okay. Well, we cannot disable begin, we need it. Naturally, to iterate. So there are other ways to iterate over elements. One is a manual iteration, which in the past I usually taught that way, to say let's initialize with begin a position, and while we are not at the end, go to the next element. And there were several years when I was asked, is there an issue when you each and every time call end? And I said no, in the current data structures we have not. So, but now we have a problem, because now we have multiple calls of end, and the question is, how expensive is end? We come to that in a moment. Well, no, let's look at that at the beginning. As we saw, begin is the position of the first element, and should be the position behind the last element. We could say, we argued, well, end can be expensive. Well, we can do a trick. We can cheat. And we do that in the filter view. And that is, end is not the position behind the last element. Well, at least not technically. We anyway don't have the elements in continuous memory. So let's just use the end of the underlying container. And that way, going from the last element to the end still can take time. Think about the last element is right in front, can take significant time. But that way, and is cheap now, really cheap now. Okay. Good. Empty roughly does the same as begin. So if we have that, and when we do something like this, we say, let's wait a minute, let's me now iterate from begin to end. End is just the position at the end. And now let's make an optimization. I call this a smart iteration, where I say, if the range is empty, return. Do nothing. Very common, I would say. Now that's interesting what that means. It means that empty, aka calling begin or doing the same as begin does in the filter view, compares with end. And that means at the end we have 2 calls of begin and 1 of end. Does it make us nervous? No. It means that checking for emptiness might cost time here. This is not the filter view as implemented. This is assume we would naively implement the filter view. So this is not what makes us very nervous. Yeah, we still have linear complexity, and yeah, it takes a little bit longer to have it twice. What makes us nervous, or the designers of this library nervous, is reverse iteration. So if you reverse iterate, that means at the end that from the outside passing your stuff to reverse maps a begin to the end and an end to begin and plus plus to minus minus, essentially, with some index issues, +1 or so. So here, now it's interesting. If you have the range-based for loop, once again, we call once begin, once end. Okay. But now if we iterate with the manual way, calling multiple times end, this will multiple times call begin. That's not good. Because for each and every element, we iterate, and then to call begin, we have to find, to compare with end, we compute begin, and begin might be just the last element, so might be a linear computation. So if your first element is the last one, this is multiple calls of begin, 1 call of end, and that means in this scenario, we grow quadratically. And that's a nightmare. We don't want to have that. Well, you don't want to have it, probably. Okay. And that's a fact. That's not theory. That's practice. You can see that I have code where I just used, where I just implemented that. Well, I took the filter view and modified it a little bit so that we just have the behavior you just saw, the naive behavior of a filter. And you see that, well, if we use a range-based for loop, which caches end, filter pipe to reverse is okay, but filter pipe to reverse, pipe to a filter gets trouble. And if we do the manual iteration, calling end multiple times, you see already filter pipe to reverse is a nightmare. It's a factor of 10,000 for 265,000 elements. And we have way more in computing, at least in mass data computing. So that's not acceptable. Let's make it cheap. And if you use the filter view, it is cheap. These are the same numbers if I use the current implementations that are shipped. Why and how does the filter do that? Well, the trick is simple. When I have a vector and I'm filtering and I call begin then finds the first matching element, and that element is cached into the view. So next time we call begin, it's cheap. It's just costs no time. And we do the same for lists. So let's here iterate over the list. We find the first matching element. We cache begin. A couple of views use caching. Filter is one of them. Some views only cache sometimes, so like drop. Some cache always for some reasons like this. There's one interesting issue, which is what happens if you cache begin, or you call it again, but in the meantime, the vector has new elements. Then we push back something. So that's interesting. We have an implementation for that says, well, the vector allocates more memory. So that invalidates the cache begin, obviously. So, but there's a trick. The trick is, if we have a vector inside or underlying under the filter, well, technically, if we have a random access queue underlying, we don't cache the position element, we cache the offset. So here we cache 3 as the offset, so that even when we have new memory, begin is cached. So this seems to be that we have great support for modifying underlying ranges after initializing the view or using it for the first time. Be careful. So let's see where we are. Declaration initialization in a filter view is cheap. Begin can be expensive on the first call only. End is cheap. Empty can be expensive on the first call. Well, it's so either way. If you first call begin, the next empty is cheap, and the other way around. And so that's the count guarantees we have. And you can see that in the standard. While we have for containers, declaration and begin and end all have constant complexity. For views, we say initialization has constant complexity, but begin and end have amortized constant complexity. Amortized sounds great, but the problem is it only is a benefit if you use begin more than once, which is not as usual as where we have amortized complexity for pushback. It's pretty likely that once you call pushback, you call it again. So it's more likely that you benefit from that. And this has a consequence even for concepts. So the requirement for concepts for ranges in general, which could be containers or views, require only that begin and end have amortized constant time. They don't require constant time. So now you saw how filters are implemented. And you think, great, we solved the issue, great performance. Now we have to talk a little bit about the consequences of this. Let's start by reading the elements in a filtered collection. That's my print, my generic print. Let's have a vector. We can pass a vector. And because we pass a container as a whole, we don't want to copy it. We pass it as const reference. What else did we learn? Now let's take the first 3 elements. Yeah, so we pass this by reference, fine. We use transform. Great, works. Now let's use the filter. Doesn't compile. Think about, without knowing anything about views, you see this problem as a beginner. You have this code. Views pipelines work great until you use a filter, and suddenly it doesn't work anymore. It does not compile. Well, now, when I had that the first time, that was when I wrote the C++20 book after it was shipped. C++20 was shipped. I tried immediately a few other things, of course, and you will also do. One is, let's iterate directly without calling print. And to my surprise, that compiles. So, okay, what is the problem? Well, let's look at the error message. Well, that's easy. Oh, is it? There's an error. this argument discards qualifiers. Those who know compilers know, oh, there's a const issue somewhere. And it is, of course it is, there's a const issue, because we make the filter view const. But we call begin, and begin caches, and that modifies the view. So that's no longer possible. You cannot pass a filter to code when you make the view const. Pass it as a const reference. That will simply not compile. Easy, yeah? Okay. What can we do instead? Well, there's one way to pass something by reference without making it const. That's a universal reference. In the standard comment here, unfortunately, we call this a forwarding reference because some arguments have been that is for perfect forwarding. That's not true. We need these references for other things, and they can universally refer to both R values and L values, and that is what we need here without making things const. The term universal reference comes from Scott Myers, so I still use it. Excuse me for that. And that is, yeah, that way it works, because we don't make the view const. So the consequence is, in all of your generic code you have written so far, replace const t reference by t ref ref. Welcome. But wait a minute, there's an issue. So you no longer pass this by const reference, you do not make it const. Now let's inside directly or indirectly call a thread that iterates over the elements. Sure, why not? As I said, could happen very indirectly. And at the same time, so far everything is safe, but at the same time, let's ask, is it empty, by the way? That means two threads call for the first time the code that finds begin to cache it. This is undefined behavior. This is a runtime error. So iterating over a view is not thread safe. Multiple times. Yeah, if you do that multiple times. Or if you in one thread call begin, in the other you call empty. So it depends. I mean, processing a vector pass to take or transform is fine, but processing a vector pass to filter, now you have a runtime error. That is a concurrent read access. That's undefined behavior. We learned yesterday morning in the keynote by Hub, we don't like undefined behavior. Yeah, we just standardized it in C++20 for a very interesting use case. Okay. Well, in this case, please use const. Const out reference, because then you see that it doesn't compile. Now, there's an interesting workaround to make this code compile. Everybody hates me about this slide that's coming now, but it's funny. You could call, before you start the two threads, you could call empty. That initializes begin in the cache, and now we are safe. Well, okay, I could use begin here, but empty is more fun because we just have no discard added to all empty places in the containers. So what this means is empty is no longer stateless. It has a meaning even if you don't use the return value. Interesting.
Are you directly expressing intent with that statement?
No, I don't say you should do that. This is for fun, yeah? Forget that. Forget that. But, you know, silly slides like this sometimes reveal design issues and show what we have designed. So, the other way is keep your const t reference going, and then you have a couple of ways at the calling side to do some fixes. So one is use a sub-range. That's a blue code on the bottom here. A sub-range at construction time calls begin. It internally it stores two members, one for begin, one for end. So we initialize a subrange and pass it to print. Unfortunately, this code, as you see it here, cannot be written in one line because of limits to class template argument deduction. So you need these two lines, and I only have to explain that to my programmers. That was sarcasm. And the other way is, yeah, let's take it by value. But now, if I pass a vector, that's expensive. But there's a workaround saying, wait a minute, let's make sure when we take the collection by value, it's a view. There's a concept for views. So, okay, so at least now we see that there's an issue when we pass a vector to print. How can we otherwise support that? Now, there's an all view creating a reference semantic API for all elements, and that is a view that can be passed. Or you can do iterating by value for views, and otherwise take a reference and then create this all view. Be careful, that's not overloading in a way that we just have something that matches better than the other. Because one takes by value, the other by reference. There are surprising behavior here. So make sure this is not for views. That's what you need there. Easy, huh? Okay. Reads. That was only reads. Now let's talk about writes. Let's modify some elements using a filter, which in principle is allowed. So let's initialize a view that says, I only accept the even elements. Let's iterate over them and add 2 to them. And you see 1, 4, 7, 10 becomes 1, 6, 7, 12. Awesome. Let's do it once again. And you see, we use the view twice, which we defined on top here. Works, fine. Good. Now let's change this example a little bit. Let's not add 2, let's add 1. Now, the first iteration works fine, but the second one has an interesting outcome. Because we cache begin in the first call. So the second view, the second iteration, starts with the second element again, although it doesn't fit anymore. But for everything else, they check and they see, no, that's not even. Okay. We are not stupid in standard. We know that there's an issue. But I'm not sure I like how we dealt with that. We said, don't do that. So we say, this is a runtime error. Well, in general, we say, it's a runtime error if you add 1 here, even in the first iteration. So the first iteration is already undefined behavior. So the official wording says this, modifications of elements of a filter view iterator denotes it's permitted, but results in undefined behavior if the resulting value does not satisfy the filter predicate. So it's easy. Done. We have done our job. We have standardized, and now it's your problem to deal with that. That reminds me, on a visit in Sao Paulo, in a high building, in an elevator, and before I entered the elevator, I saw this sign. Warning, before getting in, make sure the lift is in this floor. Done, we are safe. We have done our job. Yeah, in general, we have a wording for that. That is a put your ass on the wall paper. Okay. And there's Patrice at the end of this room. When he saw about that, he sent me a great example. He said, oh, wait a minute. I should be able to do this. When I have a couple of monsters and some of them are dead, and I want to resurrect them, bring them back to life, That should be possible, but that's according to the C++ standard undefined behavior. That's not allowed to do. You can burn them, hoping they don't get alive, because otherwise it's undefined behavior. You never know with monsters. Just make clear what you just see here. You are not allowed, it's undefined behavior, to use a filter view to heal broken elements, which is one of the top use cases you use for views and filters. What? Huh? Okay, but now you know it. I told you. So now you do it right. But now you know what I mean by taming the filter view. How do you do that? How do you deal with that? Well, to be honest, we were a little bit lazy in specifying when exactly is something here undefined behavior. The first iteration works fine all the time. So just iterate only once, and then it works. But that means you create your pipeline on the fly, ad hoc. So use and reuse views ad hoc. That's the message here. So that we only call once begin. Why do we cache begin then? Okay. Because of reverse. Okay. Okay. If you want to specify what you want to do, that has an interesting consequence. So think about, this is your code. You want to add a value to a range. And you have some values here. And the usual way you would expect to say, I want to define what to do with the elements or what to process ahead and pass it as an argument to this add function. So let me define, we take all the elements of this view, of this collection, except the first one, and take only those that have no suffix. Well, all of them have no suffix. The suffix, what I mean here is ms, milliseconds or so. And then add to all these elements ms. Same problem. If you do that twice, you have an interesting outcome. The first element is ms. How can you fix that? Because you want to specify views and pipelines in a head and pass them to somewhere else. That's possible. Instead of that, you can define the pipe without the underlying source range. That's okay to do. And if you do pass that then, separate it from the collection, or you pipe it directly in the add call, but something like that, then this is undefined behavior, but it works. Pass views and pipelines without the underlying range. Okay. Okay, we had reads, we had writes. Now let's modify elements between iterations. And you saw there's some support. We have a vector, we do something, and when we modify the vector, the cache begin is maintained. But wait a minute. So look at this code. I have a vector, 1, 2, 3, 4 are the element values. I have a list, 1, 2, 3, 4 are the element values. I just call reserve to make sure I don't have a reallocation for the vector. So now let me define vector pipe into a filter, list pipe into a filter. Now insert something new. Begin at the beginning of both. Now let's print out the values. It works. Awesome. So what this means is we print vector pipe into filter, list pipe and filter. So that's 0, 2, 4 in both cases. Let's insert 2 more elements at the beginning and do this again. Oh. Okay. -2024 is correct. Probably. 024 is at least different. So it depends on whether you use a vector or a list under the hood of a filter, and you get different behavior. That alone makes me nervous. But it gets worse. You are surprised. So what are you doing when you're surprised? You ask an expert, or first of all, you try to understand yourself. So, and what is the first thing you do? You add an additional print statement. And the whole program is broken. So look at that. 024, 024, minus 2, 024, and 024. And now with the first print, even the first output is broken and different. And now we even have non-even elements that are printed. Yeah, print or empty or other reads change the state. That's what we design. Well, the obvious question now is, can we uncache something? It depends. You can by copy the view if we cached the iterator. If we cached the offset, you can't. So you see that by copying the view and then using these copies to print out the elements, the filter on a list is fixed. The filter on the vector is not fixed. We like that. Huh? We like that design. You see, I think you see a lot of interesting use cases. And there's another thing you might not see immediately from this slide, which is think about your print elements by value. So you take the collection by value, and you can do that for a view. But you have another function that takes the collection by reference. And now let's have a set. Let's filter for even elements. Let's insert another element there. And let's call print by value, print by reference. Yeah, great. 0, 2, and 4 are the even elements. But let's check. Let's only insert 0 when the collection is not empty. So one of the two is broken. That's what we designed. Okay. So, time to sum up. We have basic idioms established for 20 years in C++ when dealing with ranges. You can iterate if the range is const. Broken for filter. A read iteration does not change state. Broken for filter. Well, sometimes it means sometimes. It depends when. And note that some of this is compile time error, some of this is a runtime error. Empty doesn't have side effects. Broken for filters. Concurrent read iterations are safe. Broken for filters. A copy of a range has the same state. Broken for filters. Something. Modifications between iterations are safe. Broken for filters. Modifications via the iterators are safe. Broken for filters. Well, don't get me wrong. If you use a filter, there are things that cannot work correctly. So if you use a filter and you're modifying elements and you get back, you have issues. But just iterating from begin to end, one iteration over all the elements, that should work, even if I have modifications, and it should work even if I, between two iterations, change something. That at least is what I would expect as a user. So what are the consequences? So how do you tame the filter view? Put filters early in the pipeline. We learned that at the beginning. Apply filters views ad hoc, which means don't pass a filter view or pipeline with the underlying range. Bring them together at the last moment. So part of everything behind the source, the pipeline can be specified. And you saw that it can even be passed by const reference. Do not modify elements in a filter. That's the best advice. Not in, not via filter, not outside. Or if you modify, do not break the predicate, which means You cannot use a filter view to heal broken elements. I think this is a severe issue. Or iterate only once from begin to end, like with an input iterator. This works as formally undefined view behavior, but okay. Do not modify underlying ranges after applying a filter, or if you modify, don't call empty front or read iterations before this modification. Do not use filters in concurrent code and prefer empty over size equals 0. Couple of consequences. There might be a last question. Why didn't we come up with another design that doesn't create so much trouble? Well, our current design between a couple of alternatives was begin as cache, which leads, as you saw, a couple of serious compile time errors. You cannot understand what a nightmare it is for me to teach the concept of const to beginners and then say, yep, wait, here it doesn't work. That's absolutely counterproductive. That is we do not respect const in views. Const. There are reasons for that. Yeah, performance and others, because the all other alternatives have other consequences. But that alone is a problem. And then all this undefined behavior, healing broken elements, trivial modifications, concurrent reads, and just adding a read changes the state of the program. I think that's a nightmare, an absolute nightmare. And they can tell me as often as they're like, yeah, you should not write these programs. Programs write programs they should not do. And they can expect that the print does not cause harm to the state of an object. Into that later. You could initialize begin at construction time. We didn't do that because that would cause that even the construction of an object, of a filter, may take serious time. So we have a performance issue here. I understand. We could say, well, do it the right way. If you cache begin, make sure it's transparent. So we have mutable for that. So at the outside, it should still be const. Well, you have the other problems, the runtime problems, and mutable itself means that we need that we still have concurrent code, and the begin would need some locks or mutexes inside. That's also not accepted. We could skip caching. Well, then a filter view would work as it is, but there would be some performance issues. Please note where the performance issues were. They were only when we applied reverse to a filter. So, because reverse changed the order, I asked, do we have any other views where this is a problem? And yeah, you can write some yourself. But no, it's not. It's only reverse. So an interesting other alternative is then reverse. Why does reverse not cache instead? So there we have the problem. There we solve it. But that means the programmer will also have to resolve issues when they themselves create quadratic complexity. But that's not too hard to do using a subrange, or we could provide a cache begin type element in the pipeline. Well, now it's a little bit too late, but because if we switch to something like no caching at all, we might, for existing code, create suddenly quadratic complexity. That's severe. That's a severe break of backward compatibility. So another option would be no caching and filter iterators become input iterators, which implies you cannot twice iterate over the elements. And You can still call empty, which doubles the time, but you don't have quadratic complexity. This disables some algorithms with multiple or reverse iterations. So some non-trivial use cases might no longer compile. But hey, how often do we use reverse? I could live with that. And remember, all the described issues you saw are gone. All of them. Thank you very much. I think we might have time for 1 or 2 questions, I'm not sure. Are you able to ask something? Yeah, come to the mic here, please.
Hello?
Yeah.
Yeah, thank you so much. Great talk. I was curious, do you recommend using filters at all in this current state?
I teach a lot C++20. So the usual reaction in companies where I teach C++20 is that they honestly think about not using views at all. And it's not only the filter view that has this problem. The drop view sometimes caches. That's even more funny what you can do that. And so that's something you have to decide yourself. But I see companies saying, we have a serious issue here. That's not something we can give to ordinary programmers. They have to know that all. When I complained about that, and those who standardize that, and they said, yeah, you should just teach it right, which I did here. And so, or you buy all 4 million programs, buy my books. That would be great. But no, I think it's a very, very realistic question whether this is not the death of accepting views to be used, at least in safety critical environments. And for that, the design is far too great to let that happen. I would love to fix that and use that as it is, just as it is. Yeah.
Thank you.
Any other question? Daisy is coming. Where?
Answer other questions first.
What? Yeah, come here to the mic, please. So whoever comes first. Yeah.
On your possible design alternatives, it seems to me you could also start invalidating intervals and validating iterators under certain circumstances that were reasonable, which would force reinitialization.
You cannot invalidate the iterators, because remember that iterators don't know where they're iterating over. It's just pointers. Or they have to know that and then understand the semantics of that. So I don't think that's a feasible alternative. Daisy.
So this is fantastic. It makes my presentation much worse. But hey, also, I actually think we could fix some of these via defect reports. I think we have to.
Great. I think we have to. We agree on that.
I think we did this with lazy split view, and I think we could do it with some of these things.
Let's talk about that.
Yeah, let's definitely talk.
So there's a paper in my on track I'm currently writing. It's not called Taming the Filter View, it's Healing the Filter View. And it will come up with a proposal about what we should do. I'm currently still discussing this with other experts in the standard committee. The problem is the group who standardized this behavior doesn't even see a problem with that.
Yeah, I chair that group. Sorry.
Huh? Now you do, or what? You do?
Yeah.
Yeah, so you're the first one in the Rangers group.
I know.
Thank you.
I know.
Thank you.
No, I mean, I think the other option, right, is to do something like we did with cache one, and be explicit about caching.
Yeah. We have to talk. We have to do our job. We have to do our job in the standard committee. You're right. Yeah.
Given that these issues exist in the current implementation, given the C++ community's fondness for backwards compatibility, are we potentially forever stuck with these gotchas?
Well, as we just discussed, we see some way to break that, we sometimes break code. When we break code, we don't want that the code still compiles, but behaves differently, both in performance and in behavior. So that's, I think it's close to a no-go. But except we exactly know that it's totally bullshit what is called here, or whatsoever. So, but we sometimes do that. Well, remember each keyword, we standardize breaks existing code that uses that as a variable name. So we can break, but we should be backward compatible, or there should be a very good reason not to be. So we had the same issue when I proposed 10 years, over 10 years to fix the range-based for loop. We finally did. And so far, nobody complained as far as I know, what even then. But the mass says, oh, great, finally, we did. Because we found out that in the code bases where we double check, is it used? We saw that all the crazy workarounds for the range-based for loop were done just because it was broken. So it was the other way around than we thought. Yeah, so I think, no, in general, in C++, we do it rarely and only for good reasons. And we definitely prefer breaking backward compatibility at compile time over runtime, but it's possible to do. But it's a big deal. It's really a big deal. I'm not sure we can do that.
You mentioned a few times about how in cases where you're iterating only once over the filter view, you're modifying the elements so they no longer fit the predicate, it is formally undefined behavior, but it works in practice.
Well, that example, there are some examples that still not work. Yeah, so if you go back and forth a lot of time, etc. Yeah.
But meaning if you only iterate once.
Yeah, so input iterators have the interesting design that they say we only iterate once over the elements. So with the filter, we decide which element to process, and then it doesn't matter anymore what we do with the value of that element. So therefore, that is conceptually safe. You do that.
So do you think it's possible to define more precisely in the standard what is and isn't undefined behavior in a way that library implementers can still fit?
Those who discussed that said, yeah, well, maybe we only have to specify more clearly when we have undefined behavior. So that one iteration with the first iteration, it's okay, but everything else is not, and not using a reverse is not, etc. I'm curious about that, but I think this is not the whole story. We have a lot of other problems. Yeah.
Thank you.
I think in defense of SG9, I think it will say that they do know this is a problem. We do know this is a problem. And
SG9 is the ranges working group.
Sorry. Yeah. Yes. And that is why to input, or it, as input or whatever we're going to end up calling it, is probably going into 26. That's why cache 1 is probably going into 26. Fix both of these problems. And if you want to wrap them in your code base, you can do that and say don't call std filter use.
Right.
But it doesn't look good in textbooks. I agree.
Okay. Last question.
Excellent. Can you turn back to the slide with broken for filters and everything?
There were many with broken for filters. You mean that one? Oh, you want to take a picture? Yeah, I leave it there. So first of all, thank you very much. Tomorrow I give a talk about concepts. That's more fun. And thank you for your attention. If you want to help me to fix that, because that's a big deal. I'm only the fixer in C++, fixing thread, fixing atomics, fixing the range-based for loop. Now I want to fix that. I think it's worth it. And help me. That's what I want to say. You can help me. Support me, because we need a loud community saying we don't want that. If you think it's not appropriate to program that way, or tell me you're wrong, Nico, which is also fine. Thank you very much.